So now on to Lenz's law. So Lenz's law states that the direction of the induced EMF or current is always such to oppose the change making it. Or producing it. So let's think about what this actually means. If we consider the most basic kind of introduction that we give you to electromagnetic induction, which tends to be a coil of wire with a magnet kind of pushed in. Okay, so let's imagine this is going to be north going in first and then south going in first. Okay, so what we're saying is if the north pole is being pushed into this coil, that's going to induce an EMF in the coil. Okay, and that EMF itself is then going to have its own magnetic field. So if we push the north pole in, we are doing work. Okay, so think back to principles of conservation of energy. If we're doing work to push in the north pole of the magnet into the coil, then what must happen is that this end must be north. Okay, so because we're doing work to push it in, and then when we pull it out, so when it's being pulled out, we're still doing work to pull a north pole away, so therefore it must be south. So when it's being pushed in, it will induce it in one direction, which makes sense based on what we know about alternating current. So if it's pushed in one direction, it induces, so this end would be the north pole in the coil, and then when it's being pulled out, it's in the opposite direction, so this would be the south pole. And then it makes sense for the same, so going in, if it's the south pole pushing in, this would be induced, so this becomes the south pole, and then when it's being pulled out, this would be the north pole. Okay, so how does this actually link to the kind of the EMF or the current? Well, you might remember from GCSE these funny kind of diagrams that we drew you, where you could have a look. If you imagined the end of the coil, that the pole shows the direction that it would be going. So if we take a roll of tape, if we imagine that this is like that last coil on here, so if it's north, can we see that the arrows are going anti-clockwise? So if it's going anti-clockwise for the north pole, then that means that if it was north, so let's make north this colour, then it would be going that way. Okay, whereas if we made it south, then it would be going clockwise, which would mean that it would be coming up and over like so. There's a really cool demonstration that I can show you, but unfortunately I don't have the stuff at home, so I'll link you a video demonstrating it. But it's basically putting, if you had a copper pipe and you put, bear in mind that obviously copper's not magnetic, but it is a good conductor, and if you put a bit of like aluminium and a magnet into it, they don't fall at the same rate. So the aluminium will fall just under the force of the gravitational pull, whereas the magnet, yes, gravity will be pulling it down, but there's also an upwards force because as the magnet falls, it's going to induce an EMF in the copper pipe, and the copper pipe is then going to have its own magnetic field, which is going to oppose the magnet that's falling down. So it falls at a much slower rate. It sounds very, very bizarre, but like I say, I'll link you a video and you can see it for yourself. So you also need to know about how an AC generator works. So if you imagine that you've got a magnetic field, so you go from north to south, and then you have a coil of wire that is turning. So if we use some post-its, so it's turning in the around on an axle in the magnetic field. Okay, so now this coil, this kind of rectangle represents how the plane of the coil is turning. Okay, so compared to the magnetic field, so you need to kind of understand the relationships with this. So the flux linkage that we've got here has a relationship where basically when the coil is like so, so it's parallel to the field lines, it goes through zero, so the flux linkage is zero. So it goes from a maximum through zero to a maximum negative through zero to a maximum again. Okay, and then for the induced EMF, it is the kind of opposite relationship. So when this is at a maximum, this is where it goes through zero. When this is at a maximum, this is where it goes through zero. So we're going to go up to a maximum when the flux linkage is minimum, or is zero, sorry, and then down to a negative maximum again, so showing it in the opposite direction. And this, we should remember this from kind of GCSE induction as well, of if we imagine where the coil actually is, it's done one entire rotation here, and so the EMF has been induced in one direction and in the other direction. So we can consider this, so this would be kind of one time period, and sometimes that's expressed in terms of frequency as a fraction of the time period. So we can think about this mathematically as well. So if we remember, so again going back to like last lesson, we know that n phi is equal to tan cos theta, and we know that this changes with time as the coil rotates. So we know from up here we could put in EMF equals delta tan cos theta over delta t, and we know that within like one AC generator that B, A and N are all constant, so then we can say that the EMF is equal to the change in cosine of the angle over time. So it's just recognising that these things aren't going to change when you're talking about one specific generator.